In case you are lost, let's have a summary. Okay. Summary of what we have seen in the last few lectures. So this is Schrödinger's equation. Okay. Right? So we propose a solution in the form propose psi of xt to be phi of x and phi of t. And then from this we separate this into two equations, right? The first one is IH bar del over del t equals to E phi. And this part, okay, we will come to that part. Okay. H so far, is this helpful to remember what was going on? So this one brings you, okay. So we have proposed this, and that way got this. Okay, so this will bring us e to the I, en. Was there a minus sign? Yes. This kind of stuff. This will bring us that. And this will bring us an eigenvalue equation, right? So you have E1, E2, E3, etc. that are eigenvalues. And phi 1, phi 2, phi 3 that are eigenvectors. Okay? And you basically represent the initial function as the sum of Cn times phi n, right? Hence, you get Cn's to be phi n star phi of x0 integral. Do you remember all this? Yes? And finally, phi of xt is n Cn phi n e to the minus I en t over h bar. That's how this quantum mechanics machinery works. This tells you what will happen to, this basically summarizes the propagation part, right? What happens to the wave function as it propagates. Do you have any questions at this point? Okay, no questions. So let's talk about these Cn's. Oops. What Cn's mean? We have already mentioned it briefly, but let's dive deeper into this. So Cn squared, absolute value squared of Cn's, will give you probability of measuring energy En. Okay? That's what Cn's are telling you. So the wave function propagates. We have already played with it in a computer. Do you remember? When we put CNs to, like, when we have, for example, let's remind ourselves. So if I start with something like this, 2 phi 1 plus, let me just make it easier for you, 3 phi 1, 4 phi 2, phi 3, let's go to 4 phi 3, and there is A. How can you find A? Let me tell you something. Before we go there, do you agree that in this case 3A is C1, right? And 4A is C2. No, C3. So remember, this gives you the probability of measuring energy En. So if it's a probability, then it has to sum up, this has to sum up to 1. Does it make sense to everyone? So what does it mean? Since there is no C2, C4, they are all 0, C1 absolute value squared plus C3 absolute value squared needs to be 1. Hence, so let's put, by the way, this is important, right? And this whole thing is also important. All right. So since this is the case, we can say that 9a squared plus 16a squared must be 1, right? A squared is 1 over 25. A is 1 over 5. Do you agree? So your psi of x0 is 3 over 5 phi 1 plus 4 over 5 phi 3. Do you agree with this? Yes.
Why A can be negative?
Very good point. Very good point. So in this course, whenever we have this kind of stuff, so indeed this is actually absolute value squared. This is absolute value squared. No, not like you are still right. You are still right in a sense that this could be e to the I theta. You can put there any e to the I theta you want, but we are not putting it there. We are just, yes.
You can show that it's possible, like writing the normalization equation again, so it will be more practical.
What do you mean?
Like put A equals 1 over 5 e to the I theta, then just try to write the normalization equation for the function. You will see that because of A complex congregate, imaginary part is always cancelled.
Should we do that? Should we do what he, yes, let's do it. So A could be anything like this, okay? And you will still have normalization. We just don't put the e to the I theta, not to confuse ourselves. Because you could have had, okay, let me just copy this one. You could have had this in front of it, right? No problem. You would still have normalization because let's take the complex conjugate of this one. Let me duplicate it twice. Duplicate and then duplicate again. So if you want to do psi star psi integral, okay, what do you have? Psi star over here is this, star is this, star is this, and you multiply and you take integral. Okay? First of all, this one takes care of that one. So it's gone already. Okay? The rest, I've never, I usually skipped it in this course, so let's do it once at least. So 9 over 25, phi 1 star phi 1. Are you following? Plus 12 over 25, phi 1 star phi 3. 16? No, okay. No worries. Now comes the 16. It's coming soon. 12 over 25, phi 3 star phi 1, plus now comes 16 over 25, phi 3 star phi 3, and the whole thing is integral. So let's look at the individual integrals. Okay? This integral, if I take 9 over 25 out, 9 over 25 out, what is the remaining integral? 1, right? And similarly, the other one is 1. This one is also 1. So 16 over 25, 9 over 25. Right? How about this one? What is this integral? 0. This integral, also 0. So you get 1. So you could have had e to the I theta, and minus 1 is one of the e to the I thetas. Remember, it was e to the I pi. But for simplicity, we just write it like this.
It's called global phase.
Which one?
The
E to the I theta is apparently called global phase. Smarter every day. Thanks to Ekin. So what we are glancing at right now, we haven't glanced at it. Let me just ask you. If I make a measurement for this wave function, let me just take this wave function. Let me go one step further. I take this wave function. This is my beginning, right? This is how I begin. How do I proceed? I proceed with this. X of t is 3 over 5 phi 1. I just add these time parts. Do you agree with this? Very good point. E3. Now, I have suggested that, so if this is moving, right? This is oscillating. What if I make an energy measurement? So I make energy measurement. What comes out? What are the probability of getting E2? 0. Why it is 0? Probability of measuring E2 is C2 squared, which is 0, right? Probability of getting E1 is C1 squared, which is 9 over 25. So 36%? 36%. Right? Am I doing wrong something? No. Probability of getting E3 is C3 squared, which is 64%. And there is no other probability. Wherever I put it, this one is better for now. Do you have any questions? Have you learned something new today? Yes? I hope so. What was it?
I cannot remember clearly, but you calculated the A coefficient the last session. Another method.
It was actually the same method in disguise. Okay, what I did before is to basically take this and equal it to 1. Okay, and when you take this and equal it to 1, it corresponds to Cn squared, summation of Cn squares being 1. Okay, all right. What is the best way for me to explain Cn's in one other way? So this is the summary of propagation, right? Summary of propagation. You start with a wave function, it propagates. And then I just said that this is what you get when you measure energy. So far, we have talked about two measurements. We have talked about energy measurement and position measurement, right? So we have said that energy measurement returns ENs with probability Cn squared, right? And position measurement returns x, some x, with probability psi of x t squared. Do you remember this? Actually, if we are going to be more precise, it's being between x and x plus dx is this much times dx. Okay? Is this better? Or did you like the previous one? Anyways, you don't care. So can we reconcile these two things in one unified way of thinking? Yes, we can, but you have to buckle up your seatbelts for that. Okay? What's going on? Let's see what's going on. And I'm afraid, to be honest, to enter this discussion in this morning, but are you ready? Let me try. So, it's all about projections, okay? Vectors and projections. So, when you have psi, remember it's a function, and remember that function was a vector in infinite dimensional, I want to say space, but infinite dimensional space, but not this space, not x, y, z. Hilbert space. Do we call it Hilbert space? Is that what it is?
Yes. Actually, you should say vector in Hilbert space, because Hilbert space is infinite dimension.
Yes. All right. So next time you hear Hilbert space, it's that infinite dimensional vector, infinite dimensional space. Why do we say so? You remember, we can still think of it in finite terms as well. So you have a function, you can still think of it as finite dimensional by putting it into a grid, and x1, x2, x3, etc., xn. Okay, then you have finite dimensional, but they all have to be perpendicular to each other, these x1, x2, x3s. I cannot draw that, right? And then in that space, there is this psi. Okay, it's pointing at a certain direction. Okay.
Psi is the summation of all of x. I mean,
Square root of size.
Psi is this. Psi is this. So what is your psi x1? It's, let's say, this much. So you go in x1 that much. Okay? What is your psi x2? It's this much, do you see? So you go this much in here, this much in here, etc. And then when you put it together, it's a vector there. It's a linear combination of certain basis. Okay, certain basis. Let me simplify it. Let's not go to infinite dimensions, but let's say somehow you have 2 dimensions. What does it mean for x? For example, you have a wave function, but you only have 2 points in space. It's a wave function that looks like this. Do you see? So then these 2 points can be actually, these 2 dimensions can be actually drawn, right? You can draw these 2 dimensions. You can say that this is x1, this is x2, and your wave function is a vector in this space. So far, did you get lost? No? One thing that we have to have is the length of this one needs to be 1. Okay? So absolute value squared of that one needs to be 1. Are you following? Yes? What do we mean by measurement? You see, quantum mechanics tells us the ultimate nature of reality is not the reality that we are living in, that we are perceiving. We are perceiving 3-dimensional space, okay? But the wave function is living in this infinite dimensional space, okay? For now, this is 2-dimensional. So whenever you ask a question to this wave function that it cannot answer, because you are asking it, are you here or are you here? Okay? So when it tries to answer, it tries to fit to your answer. Like it either falls down here and tells you that, okay, I am at x1, and now I will just be projected down there with that probability. Okay? Or it will tell you that I am over here with that probability. So it's all about projection. Now, let's say you have, okay, I'm totally confusing you. Let's say you have one measurement. You are measuring something. What letter should I write? You are measuring something, so I will write S. Okay, S2 something. You are measuring something, and when you are measuring something, you are going to get S1 with this probability and S2 with this probability. Wait, sorry, I'm sorry. That's how S1 and S2 are sitting right now, okay? Now, if you are measuring something else, let's call it E1 and E2 for the something else, their vectors might be in a different direction, right? Then, probability of measuring E1 will be this projection. Probability of measuring E2 will be this projection. It's the same wave function. But your measurement outcome depends how much shadow the wave function has on your particular basis. Okay? Shadow is projection. Shadow is just if I put light from here, where does the shadow falls? Okay? I mean projection. So Yes, now ask the question.
Said that the probability of projection, I mean, would be that psi function, psi square function. But for
I-
projection,
I didn't, I haven't come to explanation of this one yet. This one is not explained yet. This one will be explained soon. I don't know if I will be able to do it or not, but I will do my best.
you said that the probability of, I mean, x would be the psi square function. But here you said projection, I couldn't match the square function.
Let's try matching. Okay? So, this is the function, the wave function. Okay? And it has some shape. Now, let's put this wave function over here. And let's remind ourselves the energy eigenstates. For particle in a box. Okay? What are they? They look like this, like this, etc. Right? So far, did you follow? Then let's also talk about position eigenstates. How do they look like? Any ideas? Do you agree that they are Dirac deltas?
Since you are measuring them,
Yes, when you measure them, they collapse into one of these, right? Are you following? So this collapses into this and brings out E1. This collapses into this, brings out E2. This collapses into this, brings out E3. This collapses into this and brings out X1. Collapses into this, brings out X2, and collapses into this, brings out X3. So when you start saying that, where are you? You are already expecting an answer. You are already telling the wave function. I have so many political ideas right now. Can I share them a little bit? Huh? You know, this, let me just, totally different subject, okay? This identity politics, okay? When you ask someone, are you a man or a woman? The recent discussions, you know, you are basically saying that those are the two options and you have to collapse into one of them, okay? That's all I'm going to say. So back to quantum mechanics. So we are saying to wave function, there may be this infinite dimensional thing. I don't care about it. I'm measuring position. You have to fit into one of these. Okay? What wave function does? Okay, let's say you asked for position. It tells us that, okay, all these are vectors, right? So there is this vector v1, vector v2, vector v3. Are they perpendicular to each other? Yes, right? Because when you do v1 dagger v2, you get 0, right? So they are like these vectors in space, all perpendicular to each other. Don't mind me drawing as if they are not. And then your wave function is somewhere here. These are the potential outcomes of your measurement. And to find how much of a shadow you have here, over here, what you need to do is V2 dagger psi. You have to do this. Did you get it? Hmm?
The probability is V2 dagger to psi.
Yes, that's the probability.
So it's equal to psi squared.
Exactly, that's going to be equal to psi squared. Actually, can I think for a moment? This squared is the probability, right? This squared is the probability. Okay? So let's calculate that squared for measuring x. Okay? Measuring x, if you are measuring x, then your wave function will collapse into Dirac delta. Let's say you measured x3, so your function is x minus x3, right? So you want to find V3 dagger psi. You want to find the projection, the amount of projection there. How do you find it? You integrate V3 dagger, which is this one, times psi of x dx, right? Did you follow this? What do you get from this integral? Exactly, psi x3. So when you take the magnitude squared of that, you get the probability of being at x3. Did you see that? Yes? Everyone? Hocam, how about you? Yes? So let's now talk about E3. E3 is phi 3, right? So if you want to get, let's say, V3 dagger psi, then you need to integrate psi 3 star, phi 3 star, psi dx, right? And notice that this one itself is composed of Cn phi n's, and you are doing psi 3 star dx. And the only one it will pick is C3. Do you agree with that? Because every other integral will bring you 0. Mirabel? So C3, and you take its magnitude, and it gives you the probability of being at that energy.
On the letter you write V3,
So do you mean that I used V3 for this one and for this one?
Yeah.
I don't know any other letter that represents vectors so nicely. So P, Q, huh? This is just arbitrary letter. I'm trying to say that that's a vector for energy. So these are the vectors for energy. All right, where is it? These are the potential vectors for the energy. Since you are asking that question, okay, it has to be one of them. And it just calculates how much of a shadow do I have there, and it just collapses into that vector with that probability.
And why do we do this calculation in time is equal to 0?
Very good question. Brilliant question. Let's do it at time equals anything. Okay? At time equals anything, you are going to get right? What that brings out? That brings out C3 e to the minus e e3 t over h bar.
The magnitude is C3 squared.
But magnitude squared gets rid of the e to the I theta, whatever I theta is. Okay? So that's a very important thing, that no matter what time is, right? Probability of being at energy En is Cn squared, and it's time independent. Time independent. Okay? That's why. Well, there's another bigger why, but that's one of the reasons why we call phi n's, phi 1, phi 2, phi 3, the energy eigenstates are called stationary states. Okay? That's why, my dear friends, measuring energy is a special thing in quantum mechanics. When you measure energy, the next time you measure energy, you will get the same thing, no matter how much time has passed. Of course, we are talking about time-independent potential. Okay? Throughout this course, we are talking about time-independent potential. Time-dependent potentials are the whole other thing, right? But look, let's go back to this program. Goes back and forth, right? I measure position, let's say. I measure position. It collapses into a position eigenstate, and later I measure a position, I get a different position, right? So for position, for momentum, in most of the systems, you can measure something, and later on you can measure something else. But for energy, let me restore it and measure energy. So I measured energy, and it collapsed into one of the stationary states. Look, stationary state shows itself even in the absolute value squared of the wave function. It's like taking a picture of the wave function. It's just, the absolute value just freezes, okay? Then no matter how many times you measure energy, which I'm doing right now, I will always get the same energy, okay? Let me restore it, measure it again. By the way, this sameness is coming from the fact that we are using more of the first eigenstate. So let me just, you remember this, right? So let me measure energy. Okay, restore, measure, restore, measure, restore, measure, restore, measure. Yes. So right now I've collapsed into E2, right? And no matter how many times I measure energy, I will get the same energy. Do you see it? So that's why the energy eigenstates are called stationary states. Okay? Do you have any questions? Yes.
I have two questions.
Sure.
First one, in the notes, end of your notes, you wrote psi with the hat or some line on it. I'm kind of confused about the notation. What does it mean?
Previous notes.
No. I mean.
Right now.
Yeah. Can you share your notes?
Okay, sorry. I thought you were already seeing this.
That's the V3 dagger to side.
Yeah. This one just I'm trying to say that the wave function itself is also a vector. This is also a vector, but with a dagger. Vector dagger times vector gives you a number, right?
My second question is about the Hilbert space. I'm trying to match my previous information with new ones. For example, in the Laplace, you I think talked about the relation between the Hilbert space is kind of Laplace space. Not kind of Laplace space, but for example, in the Laplace space, we are trying to convert the ODEs, time-based ODEs, from the ODE to algebraic equation and solve it in the Laplace space and then come back to our time
Okay.
space. But I cannot understand the logic behind the Hilbert space. What does it do for?
Okay. So the question is, also for people to hear it, the question is, for example, you use Laplace space to go there so that the equations become easier. Okay, so differential equations become algebraic equations, and you solve them there. Then you go by inverse transform back. So that's very useful transformation. Okay. Yes, to solve something. We have the similar kind of transformation if we move to momentum space. Okay? So actually transforming wave function into momentum space is taking Fourier transform. Okay? Let's go back to our wave function. Let me just take this, copy that, and talk a little bit about momentum space. Oops. How can I? Yes. I want to paste it here. Yeah. So let me move back position eigenstates in here. Then this one could be momentum eigenstates. Okay. So your wave function looks like this. And when I say it looks like this, what I'm plotting it is in x, right? When I'm plotting it over here, position eigenstates, I'm plotting this in x, right? Are you following? So when I multiply these two, what do I pick up? I pick up this. Okay, that value, and then when I draw it, that's why I draw these lines. So that's why I'm drawing basically the same thing, right? So what I could have had is some momentum eigenstate, and momentum eigenstates look like this in x. Okay, again, I'm plotting it in x. And, okay, when I do this multiplication, I'm not going to get any value over here or over here, right? I'm getting basically the value in momentum space. So I'm taking a Fourier transform. So when I multiply it here, okay, let me just plot. Please stay with me. Stay with me. I'm pumping your heart. Stay with me. Breathe. Don't close your eyes. Don't walk towards the light. Okay? Wait. So this corresponds to a certain momentum, P4. This is eigenstate for P4. And I do this multiplication, right? And I get the value of P4 in here. So P4 is here, and I get the value over there. Do you get it? Kind of, right? It's a probability function at the end of the day. It's the square root of the probability function. Right, because you are going to take the absolute value squared. bear with me one moment, please. I could have plotted this in momentum space. Okay? In momentum space, P4 looks like this. Okay? In momentum space, P4 looks like this, and that's why I multiply these two and simply get that value. It's all about, so you see,
So position eigenvalues actually in the momentum space looks like the, just like that. Here we can also draw position eigenvalues in the momentum space also.
yes, position eigenvalues in momentum space probably also look like that. Do they though? So does a position look like this, or does it look like this? Sign mı? Okay, sorry. It looks like this. Yes, I agree. Did you get it? No? Did you get it? Yes, yes. So, do I have time? 2 more minutes. So you see, yeah.
So it means that when we measure something in momentum space, does it mean that we cannot be sure about the position?
Oh, brilliant. Yeah, Heisenberg. Yes, science. Do you know the reference? Yes, Mr. White. Yes, science. Very good, very good. Very good. We are going towards there, towards the Heisenberg uncertainty principle. Whenever position is very clear, momentum is totally unclear. Whenever momentum is clear, I think it's the time for that joke, like I stole it from someone. The electron is caught speeding, and the policeman says, "You were speeding, you were going with 69 miles an hour." And he says, "Oh, now you lost me." Yeah. Okay. Thank you very much.